Welcome to the Dam Removal Virtual Short Course. I'm Courtney Tabor from the Arctic Environmental Laboratory, and I'm glad you're here today. This short course is brought to you by the Ecosystem Management and Restoration Research Program. Throughout the course, we've been learning to characterize and evaluate potential impacts from release of sediment associated with dam decommissioning, develop an approach for screening sediment issues, and using tools to assess sediment impacts and benefits. Today, we're going to continue with a focus on assessment methods, presenting an overview of techniques to assess sediment impacts with a focus on screening level techniques, including conceptual models and screening criteria. And then we'll have a case study demonstrating application of these techniques to assess potential impacts for stream barrier removal planned for Moona Creek, New York. All right, this is part 3 of a 4-part series. And our other sessions have been archived online at the Ecosystem Management and Restoration Research Program website. And that link is on the screen here. And I can also share that in the chat in just a moment. So the recordings for part 1 and 2 were just posted this morning. So if you need to revisit those topics or share with colleagues, again, you can access those now along with the PDF of the slides shared. We've posted those at each session in 2 parts, a part A and a part B. So please check that out. There will be a part 1A, part 1B, and likewise. And then similarly, today's presentation is also being recorded, and those files will be shared once available online. I wanted to mention that PDH credits are available for attending the short course. So please email me if you are interested in receiving 1 PDH for each short course session that you attend. I've received numerous requests for those so far, and following part 4, I will tally those up and send certificates out to those who've requested. All right. Just one quick mention back to the WebEx features we'll be using. All participants are muted, so in order to facilitate our discussion and our questions throughout the session, please use the chat feature and send your questions or comments to all attendees, and we'll be able to see it. You can also select the white dot up in the upper right-hand corner of your screen and select side-by-side view for optimal video view of the presenter. All right, now on to today's agenda. We're going to, as I mentioned, we've got a part A and a part B. Part A will be an overview of tools and techniques for assessment methods presented by Dr. Lackey, and then we'll have a question and answer session for her presentation. Then we'll take a short break and begin part B today, rapid sediment analysis to inform restoration planning in Moona Creek, New York, and that will be by Dr. Kyle McKay. Then we'll also take questions for his presentation before we wrap up today. So again, use that chat feature to keep our discussion going. And without further ado, I'll introduce our first speaker today. Dr. Tahira Lackey is a research hydrology engineer at the U.S. Army Corps of Engineers Research and Development Center. She earned her master's and PhD in civil environmental engineering with a focus on computational fluid dynamics from the Georgia Institute of Technology in 2004, and has since worked at ERDC in the Coastal Hydraulics Laboratory. Her work at ERDC focuses on modeling Lagrangian transport in complex systems such as rivers, estuaries, and coastal environments to understand environmental risk due to sediment, contaminants, and man-made structures. She is the co-developer of the particle tracking model, which simulates transport of point sources in complex hydrodynamic systems. Tahira, at this time, we'll make you the presenter, and you can begin.
Thank you. Can you hear me?
I do. You sound great.
Great. So, as Courtney said, today I'm going to begin the discussion about assessment methods, and this will be sort of an introductory talk to the next 3 talks, which will focus on case studies utilizing some of the methods that I'm going to introduce or talk about today. So basically, this is going to be an overview of tools and techniques. I just wanted to show this picture to sort of talk about the fact that, all of this started, and I think Kyle mentioned that at the first week, with this dam removal workshop that we had a long time ago, relative, a few years ago, in which we were trying to figure out the state of science of things and trying to understand what types of tools and methodologies to assess sediment release during dam removal might exist. And so this is sort of a culmination of that investigation. So we've discussed over the past few weeks motivation for obviously why we're here, which is the fact that the number of dam removals has increased, and we're looking at a body of knowledge that's growing, but there are definite holes, and we really need to have a way of understanding what's available to assess or which methodologies or technologies exist, and where should research be focused to increase our capacity to understand dam removal and sediment transport in that scenario. Last week, I think Kyle and Susan both talked about these series of questions, which actually originated in that original meeting. How much sediment is stored behind a dam? What are some of the geomorphic effects of removal? What is the quality of sediment? And how do these and other factors influence permitting decisions? And today, what I'm going to do is extend that conversation with a discussion of how do we better understand and predict the impact or risk of sediment release due to dam removal. I should mention that there is a paper that we wrote for the SIDHEIT conference last year that basically describes some of our understanding that had occurred up to that point. And so most of what I talk about today, if you'd like to further investigate that, you can go to that SIDHEIT paper. So this slide, I think, has been a recurring slide over the last few weeks, and that's because it's just really quite amazing. But it talks about some of the common management concerns for dam removal, and these are some of the questions that we'd like those models and methods and technologies to answer with respect to sediment. And those are questions like how much reservoir sediment will erode and how quickly will it be transported, and also how far will it be transported. Will upstream infrastructure be affected? Will we have increased the flood level? Will the downstream water bodies be impacted? And then obviously, is there a risk to critical environmental receptors because certain suspended sediment thresholds might have been exceeded, and will turbidity influence humans using the river? All of those questions are, and many more, I imagine, are questions that we have to ask ourselves, and then that we hope that these methods and technologies will be able to answer. So before we start to talk about the methods and the tools themselves, I thought it would be good to first describe what I mean when I mention the word risk, which is something that's going to be mentioned probably throughout my talk. So this is a slide, what is risk and how do we characterize it? So risk within different subjects have different definitions, but as defined for this specific purpose, it's quantified understanding of exposure and effects. And what I mean by exposure, that is focused primarily on the sediment. Where is it moving downstream? When does it get there? Where is it exactly in the water column? How long does it take to arrive, and how long will it be at a specific location at a specific strength? Effects are what are the critical environmental receptors, such as habitat or fish migration or other biologicals that exist downstream of a dam, and what levels of exposure will negatively impact critical environmental receptors. And these levels might be acute stressors, so a quick jolt of suspended sediment concentration moving through the system, or it might be something prolonged. So understanding both exposure and effects is essential to characterizing risk. It's not enough to say the sediment is entering into the water column and reaching a specific location. We have to understand what impact that might have and if levels of a critical nature will be reached. Both of those informations are essential to actually characterize risk. Many times we spend a lot of time focused on exposure, not a lot of time understanding the actual effects. So we can use these predictive sediment transport models and tools to address some of the questions that I just mentioned, but even before we begin, there are certain important questions that we have to ask ourselves. The first question might be, do we even need a model? And I think Susan mentioned this last week when she was talking about some of the information out of the dam removal analysis guidelines, in which you have to, with an understanding of the system, be able to determine if you need a model in the first place. So that might mean if you're talking about a small dam that doesn't have a lot of sediment behind it, you might not really want to spend a lot of time trying to model something that poses no risk or might not impact the system at all based on the quality of the sediment. Maybe you don't have a lot of fines, so you know that transport might be minimal, the flow rates are low. Then even going into this, just knowing those types of things might allow you to determine if you even need a model. And then if you move past that point and you say, we need to understand this a little bit more, which models are appropriate for which type of assessment? So that might depend on how much data do I have, and then how much data do I need? Are those two the same? What level of assessment is good enough? How much time do I have, and how much money do I have? So once again, I love this quote from the Dam Removal Analysis Guidelines, and so I added it here. It says geomorphic tools should be selected in line with the project objective. So you have to understand the questions that you're asking before you can determine which tools you're going to use, as well as certain risks or concerns. I'm going to add the word concerns, the type of data and amount of data available, and the analysis time for a given removal. And then it says, furthermore, multiple tools can be applied to a single site as an analysis proceeds from preliminary screening to permit application. That means that you can start and sort of ramp up, screening level tools initially, which provide a lot of knowledge and help you to have a sort of baseline of understanding of what the system may or may not do. And then as you begin to potentially continue to another phase of your project, then utilizing that information in alignment with whatever data needs you might have to do some more extensive modeling. And this is once again a slide that I got from Kyle, in which it says, is it worth it? And it talks about the concept of model complexity relative to uncertainty in your model. The more complex, potentially the less uncertainty you have, and the greater the information quality, but also it means that the resources needed, time, funding, and expertise, definitely expertise, begins to increase. And so you have to ask yourself, what is worth it? What is that sweet spot for your project? And my favorite quote of the last few weeks is from Kyle, in which he basically said, not everything is Milltown. I love that quote because basically it means that, in a specific situation where you have a large dam with contaminants of concern moving towards the population potentially, then, yeah, you might need to do some very extensive modeling. But if you don't have, certain concerns, or if you can get the information that you need with a back-of-the-envelope calculation, then sometimes that's sufficient. So now we'll go through some categories of methods and tools used to quantify the geomorphic implications of dam removal. And you can see that this is levels of complexity from top to bottom. So first we have the conceptual models and general rules and geomorphic analysis, which I think of as common sense approaches. And then as your level of need and detail of information increases, then you might need to go further down to 1D, 2D, Lagrangian transport, and 3D sediment transport. So I'll begin by talking almost sort of in total by, or categorizing these sort of together, lumping them together, the conceptual model, the generalized rule, and the geomorphic analysis. So the conceptual model is basically just having a general understanding of the hydraulic and sediment processes in a system and using that to make some statements about the impact of dam removal on sediment transport in a system. So you might ask yourself questions like, will the system be impacted greatly due to the dam removal? How will the channel evolve due to dam removal? Do we need more modeling? So those types of questions will come from just understanding what might happen, step by step, because you understand your sediment, because you understand your flow rate. And you can look at this example of a conceptual model for reservoir sediment erosion during dam removal, and understanding of that system allows them to go from A to B. The next type of methodology is also one that I really am enjoying learning more about, and these are empirical rules. The generalized rules are empirical rules for system response to dams, and these are based on just collection of information with respect to previous dam removals. So gathering a lot of data and seeing what are some of the current trends and developing, specific equations or plots that will allow us to understand certain things. So, for example, Major et al. In 2017 said, in general, rivers converge towards stability conditions within a few years when two variables or parameters, V star and E star, have values less than 20. That's a basic statement that came from the analysis of some other well-studied dam removal. And so by just pulling that information and saying, well, when these two parameters have that specific value, then we'll reach stability condition within a few years. And that's great information to have, and they didn't have to go out and collect a whole boatload of data. They're just able to get that off of, they didn't have to go out into a specific site and pull a lot of data. They just looked at some well-studied removals. Excuse me. So generally, some of the questions that could be answered through this type of technique, well, actually the sky's the limit, because once you start pulling that kind of data, I'm sure that there are all types of trends and empirical relationships that you can develop. But definitely like things like here, like the stability and channel evolution and so forth. And the last one in this category, I suppose, are the geomorphic analysis. And I think this is very interesting because basically it says that if you have a system and you want to look at the possibility of dam removal, then look at historical data like aerial photographs and soil maps, historical accounts, all types of information about the system itself might, as well as some general site-specific information, might provide the basis for a narrative to explain what your dam is going to do when you remove the dam from the system now. So looking at what it looked like before might give you an idea of what it might look like or what the responses might look like later. So some of the questions answered here are, is there a potential for significant risk due to dam removal? Potentially if the habitat has developed over time due to the dam's existence, and then you remove the dam, then maybe there might be risk. What will the channel evolution look like generally following the dam removal? That kind of thing. So for these methods, you know, the input is going to vary, but I think that the idea is to have a general understanding, you know, of your sediment characterization, of the hydrodynamics of your system, just general, you know, what are the flows like entering the system over the course of the year, you know, just specific characterizations of your system itself. And this is, I think, you know, whether or not you do more extensive modeling, I think that these are steps that might be useful to go through no matter what. The benefits of this process are that field data collection requirements are minimum. General results can easily be focused on what your concern is despite the lack of the data. The limitations are obviously this is a low resolution type of solution to your problem. You and understand trends and what probably will happen, but it is not a true predictive model. So the next level of complexity are preliminary sediment analysis tools. And these are generally simple desktop tools. I would imagine many of them are in spreadsheets or very simple MATLAB calculations or something like that. The idea is that you're doing things like sediment budget, utilizing a sediment wave model. You don't have the complexity of a more extensive model, but this might be great for screening level, and the amount of information that you'll utilize to perform those calculations is still much more limited to some of those complex models. Here's an example of a sediment wave model results for the removal of Hemlock Dam on Trout Creek, and basically by inputting certain information into the system, they were able to determine or to predict sediment or sand deposition thickness and the distance from the dam. You know, the level of resolution, they're just saying that, you know, you're not going to, this is not a 2D model, so you're not going to get a lot of resolution, but this type of information would be extremely useful, especially at the screening level of the dam removal process. So the required input really depends on the type of analysis and what type of questions you're being asked. But the benefit is that this simple analysis requires much less site-specific data than a more complex model. Even if you don't have all the input you might need, results can be bracketed, but you can, because the model is so simple, you can run it multiple times, so you might not know certain parameters, but you can bracket them. Right? Once again, great for screening level assessment. Limitations are that this is an extremely simplified perspective of a very complex system, so it doesn't take everything into account. And, you know, you might have to run the model multiple times to get at what you're looking for. Okay, so now we're going into what I think of. I think of the previous methodologies as more likely tools or even a method. Now we're looking at what I would think of as models. So we have the 1D, 2D, Lagrangian transport model, and 3D model. Each one of these is going to require that at some certain level, a series of equations are solved. There hopefully is the ability to reproduce results and some level of validation. For a 1D model, we're talking about reach averaged hydraulic tools. I should mention that all 1D models are not the same. So when I'm talking about this 1D model, I'm looking at primarily the models that we see below, HEC-RAS, DREAM model, so on and so forth. But even with that, there are going to be differences. In many cases, we're focusing on total volume transported and reach average response. Some of the questions we might be asking ourselves when we utilize this model is, how does the cross-section of the channel change with dam removal? How does the volume change? When does the sediment arrive downstream if it's an unsteady approach to 1D modeling? We have a figure here which is an example of HEC-RAS layout. So you can see you have a storage area, and then you have a series of cross-sections. And the idea is that you can get information at each one of those cross-sections of HEC-RAS solves a series of equations. So required input, once again, I'm looking at HEC-RAS primarily because my colleague Waleska is going to be talking about modeling of the Simpkins Dam next week, and she's going to be utilizing HEC-RAS, and so I'm kind of providing maybe like a little foundation or ramp up for her talk. But the input of these, I think some of this would have needed to be the same no matter what model you use, and that's bathymetric data at each cross-section, hydrographs, which could be time series of the flow rate entering into the system, grain size distribution at the bed at every cross-section, things like sediment rating curves, and then there are some additional tuning parameters for roughness, and Waleska is going to talk about sensitivity to some of those parameters. Here you can see that we have a cross-section comparing model results to observed data. So when we begin to utilize what I consider models, then one of the benefits is that generally there is some validation approach that you can utilize to make sure that your model is working correctly. And as you continue to utilize that type of model, then the confidence and the defensibility of that modeling approach increases. I would say from our findings, the 1D sediment transport modeling is probably one of the more extensive tools or methods that are used for dam removal when we start to talk about modeling. The benefits here, once again, are that you can get results that potentially can be validated. Limitations are that in some models, the cross-sections, we still have it's still a simplified approach. Obviously, the world is not 1D. And it should be mentioned that, once again, not all 1D models are the same. Each model might have further limitations. Next, we'll talk about 2D sediment transport modeling. Now we're starting to get into a more resolved system. You can see here in the figure, which is for SRH-2D. This is a Savage Dam removal study. I should mention that this is not sediment. As we start to talk about 2D modeling and I was doing more extensive research, I began to find fewer and fewer case studies where these techniques are being utilized. I think that is probably true with most fields. As expertise grows and as need grows, I think we'll see more and more 2D and potentially 3D sediment transport modeling of dam removal. Models of this type begin to allow for a better assessment of sediment characterization, addressing the issues of bed composition transition. Some of the types of questions that now you can ask yourself are generally what are the morphology changes downstream of the dam, what are deposition and suspended sediment concentration downstream of the dam. The required input for this type of model would be sediment distribution over the entire area. You have to know what sediment already exists in the area to adequately solve the equations that you're going to be solving at every nodal point in your mesh or grid. For your boundaries, you'll need water surface elevation, velocity, and potentially flow rate, one or the other, and also bed load or suspended load for the boundary conditions. The benefits of this is that they provide spatially and temporally varying results of the deposition and erosion, and you can also, you just get more information than you potentially got from that 1D model. And we notice the equations that are provided can more realistically predict details in these complex flow regimes. Limitations are that, you know, the world is not 2D, the world is 3D. So there's still some assumptions that have to be met to utilize these models. You have to assume that the hydrodynamics are generally depth average, and that is not always the case. So if you utilize this model, this type of model, 2D model, with those assumptions in areas that where it's inappropriate, then your results will be erroneous. So, and also data requirements have increased between the 1D and 2D. And here, this is one case that I found where it looks like there was a desire to look at the potential for flooding risk downstream of a dam in Taiwan, and there was the use of the SRH2D model. Next, we'll talk about Lagrangian particle tracking. That's not something that I saw in any of the cases that were reviewed. I think that this is a definitely underutilized technique, probably because it's something that I know a lot about. But Lagrangian particle tracking basically allows the user to provide a hydrodynamic condition, introduce a specific sediment source, and determine where that sediment will go. This model is not going to be utilized to understand the morphological changes of a system or you know, the detail of long-term how a system, you know, erosion and deposition patterns and things like that. But if you want to know if there's sediment release, where is that sediment going to go, and potentially what is the potential fate of that sediment, and will it pose expose critical environmental receptors to increased level of suspended sediment, then this is a really good choice. The benefit, I should say, first, the input requirements are extensive sediment characterization, including the grain size distribution and settling rate and critical shear stresses. It uses the hydrodynamics and the sediment transport are uncoupled. So utilizing hydrodynamics that potentially you might already have or that have been developed for other purposes, you can think about, you can utilize those for a Lagrangian particle tracking model. Most systems have had some type of 2D or 3D hydrodynamic modeling done. And what it does is, as you can see in the figure here, you can determine particle path lines. So if sediment is introduced, where is it going to go? Will it potentially move in directions where you have areas of critical environmental receptors, habitat, that type of thing? Or will it move in another direction? I mean, this is just a simple way of looking at that type of system. You can also get quantitative results like suspended sediment concentration, deposition rate, and accumulation, but that requires a more extensive information with respect to the sediment introduced into the system. To date, we haven't seen this type of tool used for dam removal. We know that sediment, that it does have limitations. As I mentioned, the sediment release can't impact the hydrodynamics because they're not coupled. So this is not used to determine morphology or channel evolution or things like that. We have two examples, particle path lines, and then there's also suspended sediment concentration. All right, so 3D sediment transport modeling. This is probably the most computationally expensive, but also the technique that will give you the most information about the system. This is what will actually be utilized and will be discussed next week by Earl Hader to talk about the Milltown Dam. I believe he used GSMB for that work, and he's going to talk more about that. This is not the level of expertise in this definitely increases, but the results are that you can answer questions like, what is the systemic sediment concentration or deposition at a specific location, at a specific time, from a time ranging from days to years, and what are the morphological changes over time everywhere in the system. So realistically, you should be able to extract data all over your system in areas that are important to you, like habitat, to understand water quality, and in areas where you have concerns. And this is the just part of that grid. And remember that when we're talking about 3D, even though you have this grid, which is obviously a 2D grid, then the grid has layers. So you have multiple layers where the solutions, the sediment transport solutions, are being solved. Now, the issue with modeling, with this type of modeling, is that the data requirements are definitely more than what we've seen previously. Here, when we talk about sediment characterization, if you want appropriate results, you need things like sediment cores, which describe the grain size, density, and critical shear stress vertically. So you have cores, and you are allowed to, or you're able to determine what the grain size distribution is within the depth of that core. This will help you in your model. If you are looking at the remodeling your road sediment, you're going to need to know what type of sediment is below it, so that then when more erosion occurs, then the type of erosion, now you have a different critical shear stress with a different layer of sediment. So that type of data can be determined using laboratory testing, like SID-Flume, and I think Earl will talk about that next week as well. We'll also need sediment load data, hydrodynamic boundary conditions like water surface elevation or flow rates or velocities. The benefit of this, as I mentioned, is that at the minimum, the hydrodynamics of the model will be well validated for pre-dam removal conditions, and also this will allow users to really better understand the detailed and site-specific issues like water quality near habitat, bed morphology changes at specific locations of importance, and the results should be more spatially resolved. The limitations is that, one, we haven't seen a lot of this or at all applied in dam removal predictions, so there might be some, even as we speak, this is very computationally expensive, but, in some cases it might be worth it if you have contaminants or you have, or other concerns. This really requires extensive site-specific input data to be effective. So in summary, we can use these predictive sediment transport tools and models to address various issues regarding sediment transport due to dam removal. Generally, I'd say the biggest issue is morphology and risk. We looked at a range of methods and technologies to help categorize and understand the appropriate model usage, but ultimately determining which tool to use is dependent on your resources and the specifics of your questions and concerns. So we need to understand the data requirements of whatever tool you're going to use, the benefits as well as limitations and assumptions. And a reminder that even though we have general categories, those limitations and assumptions will be model or tool specific. So what's next? We'll be looking at a series of case studies with increasing level of complexity Kyle's going to be talking to you today about Moodness Creek, where assessment tools were utilized, and then 1D modeling techniques with a focus on the Simpkins case study will be discussed by Waleska next week, and 3D modeling techniques will be discussed by Earl Hayter next week, and he'll focus on the Milltown case study. So are there, I guess, any questions?
Great. Thank you, Tahira. Okay, so please do share your questions in the chat feature, and we'll work through those. Event producer, can you please provide instructions for asking questions over the phone line?
Yes. So as we move to Q&A, please press #2 on your telephone keypad to enter the question queue. You will hear a notification when your line is unmuted, and at that time, please state your name and question. Once again, pressing #2 will indicate that you wish to ask a question.
Great, thank you. Tahira, we don't have any questions waiting for us in the queue, but we'll give a few minutes and let people process that information and type in their questions. So please just stand by for a moment.
Sure, no problem.
All right, and I did confirm that our the videos from the past sessions are being posted. Hopefully by the end of the meeting, you'll be able to see those on the EMRRP website. So I'm waiting to post that link till I can give you assurance that the videos are accessible. Okay, we did get a question here from SHA. Are there some general guidelines on how much time and cost would be required with the 1D, 2D, or 3D modeling method? She mentioned it probably goes up with each complexity.
Yeah, I don't know if there's any general guidelines for that. You know, that is going to probably depend on how you do it. If you're doing the modeling yourself, or if you're, you know, if you're doing 3D modeling and maybe that's not your group's forte, so you contract it out, then, you know, depending on who you ask to do it, the cost obviously can increase, and then also the level of, you know, what you start with. If you already have, you know, some information of your system, then you might not have to do such extensive data collection. So I don't know if there's any, you know, I think that it really depends on the system, how much you know, what type of expertise you have, and, you know, how much you can do in-house and how much data collection even you can do in-house. All of that is going to, you know, be relevant to cost. But you're right, cost will most likely increase because the data needs, so you'll have to have some more expensive data collection, so those costs will increase. But once again, it's going to depend on who does the work pretty much.
All right, thank you, Tahira.
No problem.
Okay.
All right, we still have, oh,
yeah.
I was just going to say, we still have no questions in the queue at this time.
Okay, thank you. All right, we'll wait another minute here in case you have any other questions about Tahira's presentation before we move on.
So we might think that either I explained it very well or now everybody is extremely confused.
I think you explained it very well. Okay, we just get another question here. Do you know if there is a national database of the sediment analysis for government dams? He said, I believe that sediment analysis is collected when they conduct capacity surveys.
You mean the things like the characterization of the sediment, if you're talking about like grain size distribution and the sediment itself? I think there's actually a couple of spots where you can get that type of data. So sorry, I was actually intending to make a slide for that, but I thought it might make my presentation even longer than it was. Kyle, can you put that, you usually have these on hand, that information in the chat if you have it. If not, then we can send it out later. I mean, there's a link for that national database. And there's also another link that has been developed by the Army Corps of Engineers, not specific for dams, sediment focused on dams, but just sediment all over itself. And that's the SEGA system, which is the sediment analysis, geo something, geo app. But that was actually developed to have a better understanding of sediment characterization across the United States. And that information out as well.
And this is Kyle. During the break, I'll hunt down the link for the Corps Reservoir Sedimentation Database and drop it in the chat to everybody.
Thanks, Kyle.
Great. And Dan confirmed that you did a great job to hear.
Thank you.
All right. Any other questions for Tahir before we take a break before part 2? And producer, any questions in our phone queue?
No, there are no questions in the queue at this time.
Okay, thank you. Well, then let's go ahead and transition towards our break. If you have a question for Tahir, by all means, continue to use the chat feature. We can pick that up later. But we'll go ahead and transition towards our break. Let's plan to meet back at 2 o'clock Central Time, so in about 9 minutes. If you'll join us back, we'll kick off with Dr. Kyle McKay's presentation on rapid assessment analysis to inform restoration planning in Movement Creek, New York. In the meantime, we do have an annotation activity for you to join in on. You can select the annotation tool from the menu on the left-hand side of your screen, and there you can select a dot or a drawing tool to identify where your favorite river is located. All right, we'll leave this up while we take our break. Again, we'll start back at the top of the hour, 2 o'clock Central Time. Thank you.